work, which is background that goes into this paper. So in some sense, it's a kind of a teaching course, and I'm trying to reduce it to even school level. Calculus, differentiability, continuity, logarithm functions, things like that, but in the p-adic work. Okay, so try and get that flavor. I'm trying to give it that flavor so that it's reduced to something from at the school level. I don't know how successful I'll be, but I'm trying to do that. There are some notes which I've already written up. They're slightly long, and I'll break it into small parts and send them to you slowly. Okay, so they'll be circulated maybe by this evening. So the first lecture is on what we call the Imahori Mod P LLC, but maybe it should be called the Imahori Roy Mod P LLC. You'll see why in a second. So Shirley has also already introduced many things that go into this, but it would have been very nice if even the second lecture would have been given, because then I could have just used her statement of the Roy's Mod P local language correspondence, change it a little bit, and got the Imahori Mod P local language. So I'm actually doing the trickier thing first, and the simpler thing will come in her second lecture, but we cannot arrange everything perfectly, so there's some back and forth here. But just remember that the first version of the Mod P LLC was done by Roy, and she will talk about it, and I'm doing a variant of that. And it's exactly the same statement, but the language is a little bit different. Okay, so the Bruhatins G, which I've drawn here for FP with P equals 2. Okay, so there's a graph here with some vertices and edges. The infinite thing goes off in both directions like that. The convention in our paper is the opposite of what many people take. So usually the positive world is here and the negative world is here, right, in real life, but unfortunately the positive world is going to be here and the negative world is. So some convention we started in our paper, and I'm going to stick to it, otherwise when you look back and forth it's a little confusing, but most people don't do that. So I'm going to call this 0, 1, 2, and minus 1. So but what are these things exactly, and minus 2, etc.? And then there's some other numbers here. So when I refer to the 0th vertex, you should think of it like that. So positive and negative are linked to it. Okay, so what are the vertices of this tree? The vertices are basically lattices in QP squared. So QP came up in the last lecture. QP squared is just 2 copies of QP. It's a rank 2 vector space of a QP, dimension 2 vector space. And a lattice is a copy of ZP squared inside QP squared. But it's not just the standard one generated by the basis vectors E1, E2 over ZP. You could also take PE1 and E2 as your basis vectors, or E1, E2 over P as your basis vectors, and it's the CP span. All of these are different lattices. Okay? So there are many, many lattices inside QP squared. And this counts all lattices. It's a picture of all the lattices, but there are too many of them. So what you do is you put an equivalence relation on the lattices, you go up to homotheity, so 2 lattices are the same if L and L prime are the same if they differ by a non-zero constant. So if L is equal to alpha times L prime for alpha some non-zero constant, and then basically the 2 lattices are the same, you can scale one to the other. Okay, so these are homothetic classes of lattices. L equivalence relation. L is equivalent to L prime if L is equal to alpha times L prime for some non-zero alpha. Okay, so basically it's all lattices. Now what are the edges of this tree? So we have 2 lattices here. Some lattice, you can think of this as the standard lattice spanned by the vectors 1, 0 and 0, 1. Okay. This for me means the lattice spanned by P 0 and 0, 1. Okay. So that's what this notation means. This is P squared 0 and 0, 1, right? That lattice. But okay, we'll come back to this in a little bit. So the edges are going to be So what I was trying to get to is that every time you have two lattices which are finite index, the index will be a power of p. Whenever the index is p, then you join them by an edge. This is a bit subtle because this is not a directed graph. This is an indirect. There's no orientation on the edges yet. So you have to check something that this containment relation is symmetric, right? Okay, so let me write this down. So we say that there's an edge. This is supposed to be a long dash between two edges if EL is sitting in L prime, sitting in L. So some representatives. So L is isomorphic to ZP squared and PL is isomorphic to PZP squared, which has index P squared in here, right? Because the index is Z mod P cross Z mod, and the quotient is Z mod P cross Z mod P. So index is P squared. If you have something that's strictly between the two, then it has to have index P in here, right? This has to be index P and this has to be index P. Right? So we're basically roughly looking at lattices with an index P inclusion relation, index P containment relation. But that's not so well defined because there's no edge arrow pointing one to the other. So you have to check that this relation can also be done with this L and L prime fifth. Some of these small checks I'm not going to be able to do here. I actually gave this one of our lecture in Ahmedabad and it took me 5 hours when I was doing the small checks. Okay, so you check some of these little small things, there are many of them, when you can. Maybe in some of them in the tutorial. Okay, so now I'll follow some of Shani's notation, which is some universal notation. We let G be GL to QP. K is also her notation, GL to ZP, GL to ZP. I can say both. And I, which was not in her lecture, there was something called I1. I think I was not there. So I is the famous Eva-Hori group, which I was always very scared of. But it's good Carol is here. He will be our psychiatrist dealing with Eva-Hori. So last few years, we tried to write papers using the Eva-Hori language. And I guess this is a coming out series of lectures where we're getting over the fear of the Eva-Hori. So here we have I, which is all matrices in GL2ZP, which mod P are upper triangular. Okay? So these are three very important groups, and they'll show up all the time in these lectures. There's also some mod P versions of these. I mean, like Shani said, GP, GL2FP and things, but we'll come to that later. Right now, we just... Okay, so here is the lemma. And it says that G mod KZ, oh, I didn't define Z. So Z, I said there were only 3 groups, but there's actually one more, which is important. And I'll do it over here. So it doesn't fit in that sequence, so let me do it over here. Z is equal to the center. Okay, so it's all diagonal matrices A0, 0A, where A is not 0. Okay, so that's a copy of QP squared because AA is repeated. So that's the center. So G, this coset space, is equal to the vertices. And the second part of this, which is why we introduced the Eva-Hori, is that the coset space of IZ, so cosets of IZ is equal to the edges. Okay, so why? So every time you have a lattice to basis vectors, you can make your group GL2QP act, right, on 1, 0, and 0, 1, for instance, and take it to A, C, and BD, the column vectors of your matrix, A, B, C, D, right? So GL2QP acts on lattices, and it acts actually transitively on lattices. Given any two E1, E2, and an F1, F2, you can always find a GL2QP matrix which takes one to the other, right? So because of that, we have an action of G on the vertices, because these are, right? So the action is transitive. slowly at the beginning. Let me write this. So the action is basically this action, G dot L, which I'm not defining, but I just said it orally, right? Given two basis vectors, you can move your basis vectors around by a matrix of G and QP. But here we have homothetic classes. So why is this well defined? So that's a little small check, one that I can do on the board without getting nervous. So why is this well defined? Well, if G acts on Z times L, right? Because if L is a lattice, then Z times L, where Z is in center, little z is in capital Z. And that's also a representative, but this is just G times ZL, but since you're in the center, this is Z times GL, which is GL. Right? So if you change your representative a little bit, that doesn't change the action of G on your vertices. Okay, so this is one of the easier checks, and there's many things like this that you can keep checking. Okay, and what is the stabilizer? Well, what is the stabilizer of 1, 0, 0, 1? 1, 0, comma 0, 1, those two vectors is going to be exactly GL2ZP. Okay, so but now we're working with homothetic classes, so you also have to throw in the center. So the stabilizer is stabilizer of standard lattice E1, E2. This is 1, 0. This is 0, 1. Is exactly A, GL2ZP. I mean, I should say that you get another lattice, but if the lattice, for example, is sitting in the original lattice, the index that you get is the determinant of the matrix, okay, right? So these are some standard things. And if you're GL2ZP, the determinant is a unit, so, right, the absolute value is just 1. So, yeah, this will be, GL2ZP will be the stabilizer, and the center is acting also trivially because we're looking at homothetic classes lattices, and this is exactly right. So by the usual theorem on group actions, G mod Kz is exactly the vertices. And you can do exactly the same proof for edges. It's just a little level, one level up of being more complicated. So this time you want to specify edges of the tree. But edges are going to be, oh, I made a slight mistake here. Let's come to it. Edges, in fact, this time we want to take oriented edges. So it's not correct, the second statement. Okay, so this time we are going to put orientation on the edges, and we're going to show that G acts transitively on pairs, tuples of two lattices, of the class of lattices, and the stabilizer will be exactly IZ. So similarly, G acts transitively on pairs of lattices, pairs of homothetic classes of lattices. So the first entry in each tuple is the source, and the second entry is the target. The action is really not being defined here, just notation. So GL is where the action is really hiding, but it's just some. Right, so you have source and a target, source lattice and a target lattice, right? So this ordered pair is an ordered tuple. This is the source vertex and the target vertex written in that order, never in any other order. And G is acting on this. Now it's a little bit of a check to check that this action is also transitive. So it's one thing to say that you can take any lattice to any other lattice, but can you take any two lattices to any other two lattices if the index is P, right? So the index P containment here, you have to get an index P containment to that, and that's also true. So So it's another little check. And the stabilizer, yeah, the well-definedness, I have it in my notes again, but it's something very simple, so similar to this, so maybe I won't do it. Again, it's well-defined, it doesn't depend on the representatives here, right? You put a Z here and a Z prime here, a GZL and a GZ prime L prime, but the Z commutes past the G, the Z prime commutes past the G prime, and pulls out all the way so that you get the same thing, right? Little check there. That's independent of the homothetic class system? Yes? So when I write it in ordered pair, there are two lattices, but this is coming first and this is coming second, so that means you're going from the source to the target. So this lattice is some lattice, let's say this one, and that lattice is the other one, so we're pointing the arrow that way. Okay? A comma B means you point from A to B. Opposite also a pair, and it's pointing the other way. Okay, so those are orienting edges. And yeah, now I have to check what the stabilizer of the standard edge is. So I'm claiming the following claim. IZ is the stabilizer of the standard edge I'll write over here. Let me call it, I don't know, yeah, Zp squared and alpha Zp squared. So what is alpha? Alpha is this matrix, 1, 0, 0, P. So I think I said something a bit wrong. I think here I want to take E1 and PE2, and E1 and P squared E2, but okay. Alright, so this is an edge which is starting at the standard lattice, 1001, that's over here, and it's pointing to this one. Okay? So this is this lattice, this edge here. Because it's E1 and PE2. Right? E1 and PE2. So we have this edge. So why is this true? Okay, so let's check this. Okay, so proof, say, suppose you have G alpha, right? Make G act on this, so G Cp squared, G alpha Zp squared. Suppose this is equal to Zp squared, alpha Zp squared. Yeah, so suppose you have some element G of G, and G dot this thing is equal to itself, right? So G dot at edge is this edge. Suppose it's equal to itself. So we get two relations. Let's unwind those relations. So by the first remark, the stabilizer of Zp squared, by the first part of the proof, the stabilizer of Zp squared is just Kz, right? So this being equal, these two being equal, implies that G belongs to Kz, right? But you also have another thing here, G alpha Zp squared equals alpha Zp squared. So what does this say? This says that alpha inverse G alpha, let me do it slowly, G alpha L equals alpha L implies that alpha inverse G alpha L is equal to L, and this, by again the first part of the proof, implies that alpha G alpha belongs to Kz, right? Where L is the standard lattice, sorry, L is Zp squared here everywhere, right? Take the standard lattice, you get this. So what does that mean, putting both these statements together? putting these two statements together, we see that G belongs to both Kz and this conjugate thing, alpha Kz alpha inverse. And a little bit of a check again, which you can believe here, is saying that this is the same as Kz intersected with alpha. Oh, yeah, that's right. Yeah, K intersection. I want to put the Z out. K intersection alpha K alpha inverse Z. Okay, so one of these inclusions is obvious, maybe from here to here, but the other inclusion requires a little bit of a check, doing some determinants. And this group is another way to write the Avohori. So you can check that by conjugating some matrices. That if you conjugate your matrix ABCD by 1P on this side and 1P inverse on the other side, right? You'll get some matrix, but if it's also in K, that puts, because you'll get a PC in the lower left corner, right? So that forces, since the matrix is also in K, the B over P part in the top right corner is integral, that's some condition, but the lower left entry will be a PC, and that shows that 1P, that's 0. Okay, so it's a little bit of check to check that when you do this, you get exactly the Avohori matrix. So one of those small checks. Okay, so good. So we now have this, and this is the end of the proof of the lemma. Again, GX transitively on pairs of edges, and the stabilizer is exactly IZ. Okay, great. So now I want to talk about Hecke algebras, and I'm going to make table here. So even though some of you are learning about the spherical Hecke algebra maybe for the first time, even not for the first time because it hasn't come up yet, it's going to come up soon, I want to make this table from a world that many people work in the mod P world, to maybe a world where fewer people work in. So spherical Hecke algebras and Avohori Hecke algebras, and show you many parallels, similarities in the definitions, etc. Some of these things were done by Shalini in the spherical world, but I will resave them in the Avohori world. So I'll start with VR. So you need a weight. So VR is a little bit from Shalini's notation. It was FR0 in Shalini's notation, FR comma 0, but let me just define to be VR instead of writing FR0 everywhere. So this is the symmetric Rth power. One more difference between Shalini's notations and my course is her E was a characteristic E field, it was FP bar, but my E later in the course is going to be a characteristic 0 field, so it's going to be a finite extension of QP. That might cause some confusion, so I'm pointing it out at the beginning. So I don't have an E for now, I just have FP bar, but this is what it was her E squared. Yeah, so we take this for 0 less than R less than equal to P minus 1. So this was the range of R's for which this representation was irreducible. I'm not twisting by any determinants here, right? Just taking something a bit simpler, and yeah. So here's VR on, yeah, maybe I'll say a little bit more on the spherical side and then go back to the Avohori side. So on this you have an action, as Shalini mentioned, of GL to FP. So GL to FP is sitting in GL to FP bar, and GL to FP bar acts on the, oh yeah, so this is polynomials. I also mentioned this, but I'll repeat it. So these are all polynomials. You know, many of these things boil down to very simple things. So this Langlands stuff is some graph theory, some linear algebra, some polynomials. You know, some things that you've learned in school are very much prevalent everywhere. And you can, it sounds very fancy, the Langlands program, but many of the computations involve very simple things, graph theory and some polynomials. So keep that in mind when you're approaching this subject. Yeah, so it's all polynomials, Pxy, of degree R, homogeneous of degree R, over Fp bar. Okay, so it's all polynomials of degree R into variables, the coefficients in Fp bar, and the action of a matrix ABCD is what she wrote last time. She wrote alpha, beta, gamma, delta. I won't repeat it. Basically, it's by the column vectors, x goes to ax plus cy and y goes to bx plus dy. That's how a matrix acts on these polynomials. You substitute in the polynomial, expand out, you get another polynomial. So this becomes a representation for GL to FP. Even GL to FP bar, but we just need GL to FP. And K, GL to ZP, if you go take a matrix with entries in ZP, then you can go mod P and you get GL to F. So K also acts, because K maps to GL to FP, which acts on these polynomials. You want me to repeat the action over here? Yeah, I have it in my notes, maybe I should. Via A, B, C, D of P of xy is P of ax plus cy, comma bx plus dy. Okay, so I haven't gotten to the Heck algebras yet. I have just started doing some very simple representation theory. Here we have in a weight, GL through P is acting and K is also acting. And we're going to make maybe one minor remark here is that we're going to make PP, this diagonal matrix, act trivially. I hope you can see this. So therefore KZ acts on VR. So in the center, there's these matrices A00A. The unit parts, when you have a unit there, that's part of K anyway, so you don't have to give a new action. But when you have a non-unit element like P, then you have to say how that acts, and P is just going to act trivially. You make that thing act trivially, so it's not very interesting as far as the center goes. All right, so that's the action of KZ on VR. So let's do something. Let's now make IZ also act on some space. So over here, we're going to define D to the R. So this is going to be a character of the Borel of FP. So this is, I think in Shadi's notation also called B, but I think she had it characteristic 0, but these are all upper triangular matrices A, B, 0, D with entries in FP, right? Everyone knows the Borel is upper triangular matrices A, B, 0, D. So I write B of FP instead of B of QP, which was in her talk. Again, we're going to assume that 0 is less than R is less than equal to P minus 1. Very important. So here, I had assumed R is in a small range. Here also I'm going to assume R is in exactly the same range. And so what is this character? This character is just taking A, B, 0, D to these BR. But this is also get a character of I. Character of I, since I surjects onto B of FP, right? The definition of the Borel was when you go mod P exactly, the definition of the Ohori was when you go mod P exactly get the Borel matrices, right? So I surjects onto B of FP, and therefore you can compose this character DPR all the way from I, yeah. Yes, I want the P minus 1, that's a very important part of this talk. So even though that's repetitive as far as the character is concerned, it's going to be important for this talk. That's a very good question. It crossed my mind also that somebody might ask it. So here, as Mihir is pointing out, when R is 0 or P minus 1, when R is P minus 1 or 0, these are very different spaces. One has dimension 1, trivial representation, R equals 0, and when R is P minus 1, that's a P-dimensional space. Polynomials that P minus 1 is a P-dimensional space, right? Because you have that extra x to the P minus 1 all the way to y to the P minus 1. It's a P-dimensional space. Those spaces are quite different, but when you have a character, the two characters are the same when R is 0 or P minus 1. Okay, but I really want to include that throughout this lecture. Okay, so this is also a character of I because you can pre-compose this character with this projection from I to B of FP. So now we have a representation of I, here we have a representation of K. So parallel words, and again I think you want to make the center act trivially. One has space to write it. Get a representation. I'll just write get a representation of IZ. Okay, but here I mean that PP acts trivially again. Okay, that matrix PP acts trivially. I don't have space to write it here. Okay, good. So now we have two parallel worlds progressing at the same time. We have representations of K, 1P representations of K, P of them, are symmetric powers. And we have also p characters, which is repeated as here pointed out, characters of the Ohori or even characters of IZ. Okay, so let's continue. This discussion will go on for a while. So, making the columns, the Ohori Heck algebras. So as Shalini defined in the last lecture, once you have a representation of a subgroup of G, KZ is a representation of a subgroup of G, and IZ is also a representation of a subgroup of G, you can induce them up to G to get representations of G. Okay, so let's do that parallelly. One of the advantages of doing both of these is you will see them twice each definition in a slightly different context. So we have compact induction. I think Shalini just wrote a little I here in our top. Smooth induction was the capital I. But just to emphasize that is compact induction, once in a while I'll write the C and I'll start dropping it. That means the functions are compactly supported modulo KZ. So I don't have much space here, but it's functions from G to VR, just to see it twice, such that f of kg equals k dot f of g for all k belonging to kz and all g belonging to g. Right? And then I'm dropping the condition that f is compactly supported mod kz. Okay, we can write it. Plus f compactly supported mod kz. Not important in the first version of this. Right? These functions are supported only finely many cosets. We saw in her notation, square bracket notation, something was supported on only one coset. Okay, so we have this, and on this side also we have something similar. So we have compact induction, IZ to G, D to the R, which is all functions from this time G to D to the R. D to the R means the vector space FP bar. This PR here means the one-dimensional vector space with the action of I by D to the R, such that f of IG, I is in the Ohori, is the D entry of I to the power of R, maybe bar, times f of G. Again, f compactly supported mod IZ. Compactly supported mod IZ. Okay, so what have we done so far? We've come up with two subgroups, KZ and IZ. We have two representations for each of them. We've induced each of them. Okay, we have a big representation now of G. A bigger representation, a representation of G. Square bracket notation on both sides. So Shalini defined it as 1 comma x. Let me call it G comma V. Okay, so obvious notation here. G and G prime are in capital G, and the vector V is in VR. Okay, I won't write that down. So this is a function, right? Example. Here's an example of this compactly. This is an example of an F. How does this function act on a G prime? It basically does G prime G acting on the vector V. If this makes sense, the only time it makes sense is if this group element is in KZ, then only you have an action on V, and it's zero otherwise. Okay, if this doesn't make sense, G prime G is not in KZ, then you don't have any action of KZ on V, right? You only have action on KZ on V to the R, and not of a bigger group. You vary. So this is the definition of this function. And similarly over here, we define double square bracket GV, exactly the same notation, but to distinguish it from the spherical world, we'll define it with a double square bracket of G prime to be G prime dot G of V, exactly the same definition. G prime G belongs to IZ this time, and it's zero otherwise. That's true. That's true. These functions satisfy some nice little properties. So as you're pointing out, g comma v is also g dot 1 of v. And another nice thing is gh comma v is g of hv. You can move the h from the right here to the left here, right, or g to the left here, if h is in kz or in iz. So there's some elementary properties which come from the definition of the function. Did everyone understand this? Maybe I didn't pause here long enough. So this is just functions to a one-dimensional vector space over F3 bar. I is a matrix in iz, right? It has an A, B, C, D, and G. If you take the D entry and go mod P, so D of I is the D entry of I. Go mod P, you get a mod P thing, mod P number, and which will find the field raised to the odd power. It's a scalar, and you multiply by this other scalar f of G, right? Which is an FP bar. So it's just functions satisfying these kinds of things. Okay, so these are the typical functions in this space, and they span this space, form a basis, etc. So we have this kind of notation. Double square bracket notation is probably going to be used more in the proofs in my notes, which I may not be able to get to all of them. But if you do look at the proofs, then you will see some single square brackets and some double square brackets. And then you can try and follow the proof. Okay, so Hecke algebras. So we haven't come to Hecke algebras yet. Unfortunately, it's at the bottom here, but so this is a representation of G, right? Is everyone understanding, following what I'm saying? We started with a representation of kz, we induced it, so we got a representation of G. Why is this a representation of G? These functions only have a property on the left. There's no property on the right. So if you make the group act on functions by right translation, then that preserves this property on the left, right? So this is a natural module. I think she mentioned all this, so that's why we skip this. So this is a natural representation for G. That's the action of G. Okay, and so this is a G module. And P bar G module, so bracket G module. You could look at linear maps, right? Vector space maps from this vector space, compact induction vector space to compact induction vector space, which also commute with the G action, right? So capital T of GF is G dot ETF, capital T of F. T is linear transformation, right? So this notation NG means self maps as a G module. Okay, so we have this space, and this is the official definition of the Hecke algebra, one of the definitions. So this is the Hecke algebra, and it turns out, this is a little few pages of computation, it turns out that this algebra is actually just a polynomial algebra and generated by one operator, the famous D-Hecke operator. So this algebra is isomorphic to FP bar square bracket T. Okay, and what happens on this side? Well, so this is called the spherical Hecke algebra, maybe, as to distinguish it from the Avoharic algebra. So here we have the Avoharic algebra. It's exactly the same definition. So maybe I should write this up here. Unfortunately, I won't have space to write it here. Softer, reach enough to know these things, so that I don't have to raise the board so much. So over here we have, so that was the spherical Hecke algebra over here. Here's the Avoharic algebra. So we take and G again, same thing, but we take compact induction from the Avoharic world. I is G D to the R. I'm just going to call it D to the R, but maybe it's D bar to the R. Okay, so this is the Avoharic Hecke algebra. Spherical Hecke algebra was a polynomial algebra in one variable with this operator T, which I will tell you a little bit about in a second. And let me first write what this is. So it's also a commutative algebra in most cases. is the case where R is not equal to 0 or p minus 1. And there's a relation here. So it looks like a free algebra, but there's some relations. And the relation right over here outside, it should be inside. But t minus 1, 0, t 1, 2 is equal to t is equal to 0 is equal to t 1, 2, t minus 1, 0. Okay, so it's a bit more complicated than the usual Heck algebra. It's not a polynomial algebra, first of all. I mean, one variable, it looks like a polynomial algebra in two variables, not even a polynomial algebra in two variables because there's one relation, right? The quotient of a polynomial algebra in two variables, what will these relations? This is commutative so far because R is not equal to 0, p minus 1. So here you can see these things are commuting, it's 0. But I'm coming to the non-commutative case in a second. And if R is 0 or p minus 1, then this is the algebra that's a bit more subtle. So I'll define all these operators in a second. So notice there's a t minus 1, 0, t 1, 2. You can try and guess what these are because I made a tree and there were some vertices on the tree, right? 0, 1, 2, etc., minus 1. So because of that, these numbers will come back there. So t1, 0 and t1, 2, again, there's a comma between the 1, 0. I might forget the comma sometimes, just to be a little fast. But here there is a relation, and the relation is, there's a relation which is t1, 0, t1, 2, t1, 2, t1, 0, t1, 2 is equal to minus t1, 2. Okay? This is if there's one Heck algebra here, another Heck algebra here. This is if R is equal to 0 or p minus 1. Now there's one more relation, there are two relations. There's another relation, and that is t1, 0 squared is equal to 1. I hope you can see this with all the double writing over the board. Okay, so this is a bit confusing, and when you see this first, you think I don't want to enter this subject, it's already too technical for me. But I want to relate all of these to the graph that we drew at the beginning of the lecture. Okay, so I'll do that in a second. First, let me write the formal definitions of these down and then relate them to the graph. So there are three operators, okay? So here there's just one operator t, which I'll define in a second. And here there are basically two operators, t minus 1, 0, and t1, 2. These are important ones. But here there's a subtlety. You drop t minus 1, 0 and replace it by t1, 0 and t1, 2. Okay, and if you're wondering what happened to t minus 1, 0, I'll make a little note here. You can recover t minus 1, 0 from the following identity. T minus 1, 0 is equal to t1, 0, t1, 2, t1, 0. So those two operators, t1, 0 and t1, 2, they actually recover t minus 1, 0.
What is that t minus 1, 0?
These are just some abstract Heck operators right now with some relations, but I'll define them in terms of the edges of the graph in a second. But to answer your question quickly, t1, 0 is flipping the edge, t1, 2 is the kind of source or sink operator, and t minus 1, 0 is also the opposite, sink or source. So I have to think about it in a second. These are source and sink operators, and t1, 0 is a flipping edge operation. Okay? I think I wanted to say here that this algebra is commutative since you asked, but this algebra is not commutative because if it was commutative, you could move this t1, 0 past the t1, 2, and t1, 0 squared is 1, right? And you get this identity t minus 1, 0 equals t1, 2, which is not true. These are, they're different. The source and sink operators are different, as you. So maybe the other ways to see it which are a little better. But this is a non-commutative algebra, okay? A non-commutative Heck algebra. And it's often sometimes excluded in the literature. And I think in these lectures I want to focus a little bit on that case. So I put some references at the beginning. I should have said that all this work here is not mine. It's due to the famous ABC conjecture. It's been proved now. So there's Anand Vardhan Borissagar, not the Mochizuki ABC conjecture, but Hori ABC conjecture. So one can analyze the structure of these Hecke algebras, etc. And this has been done by, and rewrite some of the models of the supersingular representation that came up in Shanti's talk in terms of this Evahori language. And this was done by Annavardhanan and Boris Sagar almost 9 years ago, 10 years ago now, in a Journal of Algebra paper, which I written on the board at the beginning. And that's the cases where R is not equal to 0 and p minus 1. And when R is equal to 0, p minus 1, they let that case out for some good reasons. It's a bit more technical, but I will focus a little bit more on that in these lectures. Because you can try and redo all their work using some hints from them and some new things. And this was done by Anand Chitra, so that's a C. And so at the end of this, I'll have a theorem ABC, which will put together all this stuff and sort of the content of this lecture. That theorem ABC allows you to rephrase the Roy's mod P local language correspondence in terms of the Evahori language, and so we will get the Evahori mod P local language correspondence. Okay, so that's the plan for the next hour or so. Less than an hour, much less than an hour, 40 minutes. Okay, so definitions of the Hecke operators. So here, maybe I'll do it here only. So what is T of a function GB, right? Because T is, we said that this Hecke algebra is generated by one thing, so it suffices to say what T is on a particular function. Okay, so here's the formula. It's the sum. These are formal formulas which don't make much sense when you first see them, but they can be motivated using the T. So I'm going to write for my vectors, I'm going to start writing polynomials, because remember, for the spherical Hecke algebra, the vectors were polynomials, right? So T acting on G comma V is G P lambda 0, 1, P of X minus lambda X plus Py. Okay, so that's the definition of T acting on G comma P of Xy. You kind of do something in the variables here. Plus another term, G alpha P of Px comma Y. Okay, so this is the definition. I hope everyone understands the definition. You're basically multiplying on the right by some matrices. Even though lambda is in FP, this matrix doesn't make sense because G was in GL2QP. But this is what's called a type. This is a notation that I'm not going to do in these lectures because there are a lot of square brackets involved. So technically, there should be square bracket of lambda, which means you lift lambda from FP to ZP. Okay, so there's something called the typular representative. It's a root of unity which maps to FP. You can ask about this in the tutorial. So I'm not going to. Otherwise, the blackboard's already pretty complicated, and there are many square brackets. But it's clear from context almost always. So here lambda is in FP, but here lambda is not in FP. This lambda is in QP, actually in ZP by taking a lift. So those abuse of notations I will do. And one more thing I want to point out is there are P terms here because the cardinality of this field is at P. One more term, P plus 1. Right? So this Hecke operator has a degree P plus 1, which should be a little bit familiar because in the tree there's a famous operator which is given functions on the vertices of the tree, compactly supported function on the vertices of the tree. You can define a new function, T of F, that is the original function, by looking at the sum of neighbors of the values of that function. Right? So every function has a bunch of neighbors, every vertex has a bunch of neighbors, and you can sum up the values of the function and the neighbors and add them all up. That gives an action on the compactly supported functions on the tree, on the vertices of the tree. And how many neighbors are there? Well, this is a very common entrance exam problem at TIFR, for instance, which I think I troubled people in Ahmedabad with 2 weeks ago. Right? How many lattices are there inside C Z squared of index P or index 2, let's say? Everyone knows that there are two lattices, 2Z cross Z and Z cross 2Z. Right? But there's a third lattice, the diagonal lattice, the set of all x, y, such that x is congruent to y mod 2, both x and y are even and both x and y are odd. That also forms an index 2 lattice inside Z squared. We check that in the tutorials, and that's the missing third lattice, and so the valence number of lattices of index 2 inside Z squared is 3. It's P plus 1. Turns out that the number of lattices inside Z squared of index P are again P plus 1. the ZP for arbitrary p matches p equals 2. And if you work with ZP, which is the local version of Z, then again there are p plus 1 lattices in sec ZP squared. So in the valency of that graph, in the Broughart-Yates tree, there are actually p plus 1 edges sticking out from any particular vertex, right, p plus 1 neighbors. They're all the lattices of index p plus 1. And that Laplacian on the tree, famous sum of edges, sum of neighbors operator, is very much related to this T operator. Okay, T also has degree p plus 1 and that function of the graph. So this is like advanced graph theory if you want to think of it. All these Hecke operator things are basically some operators on graphs. Okay, so we'll try and make that a bit more specific in a second. Let me write the formal definitions down here of t minus 1, 0 and t1, 2 and t1, 0. So do I have space to do this without making it messy? Yeah, maybe. So t minus 1, 0 GV is the sum, oh, I don't have much space. Okay. Lambda belonging to FP. G, very similar, P lambda 0, 1, comma B. We just made it. Lambda belonging to FP. Let me write them down first. G1, 2, GV is equal to sum lambda belonging to FP. G1, 0, P lambda P. P. So this is the other side of the vertical line, right? So everything is square bracket now. All these are functions. They have a Horry world. And finally, t minus 1, 0 of GV. V should be a polynomial, but since I don't need the x and y right now, I'm just writing it without capital P's. So beta is this matrix. It's like alpha, but it's the anti-diagonal matrix 1, 0, 0.
Last map T10.
Sorry? Sorry. The last one is 1. Yes. Just erase the minus sign. Great, thank you. Okay, so now I think I've formally defined the Hecke algebra and the action of the Hecke algebra on certain kinds of functions. But these are complicated formulas which are coming from very simple things. I don't know how much time I'll have to explain them. I'll try. Okay, great. So I think I'm done with that parallel development, the definitions of the Hecke operators on both sides. Maybe I'll erase that title, go a little bit higher. Okay, interpretations in terms of the tree. So we have these complicated formulas here. Let's try and unwind them in terms of the tree. So for that, I'll just do a simple case, and that is the case of some extreme cases. So note that if you take the case R equals 0, I'm dropping a packed induction of the C. Let's take the case R equals 0 on the left. So these are functions from G to V0 with some property, right? A11. R is 0, so you basically have functions from G mod KZ to the tree. Right, because it's a trivial representation. KZ is acting trivially, so it's just the trivial representations to FP to V0, which I wrote as FP bar, okay? Here's a very simple case, the case of R equals 0, which should have been done first, but we did all R at the same time. So these are functions from G to V0, which is just trivial representation FP bar. KZ is acting trivially, so f of h dot z or k dot z is just f of k dot g is just f of g, right? Because k is trivial. K comes up, that's trivial in the trivial representation. So it's factoring to k. Corner bar. And this is these are a certain kind of cosets. I think these are right cosets, right? I have some dyslexia about this. These are right cosets, right? But in that first lemma, I'm coming back to the beginning of the lecture, there were some left cosets, right? If you remember, I was very careful to put something on the right side, on the correct side, right? There was G slash KZ, and here is KZ slash G. Okay, so, but as you know from your undergraduate classes, if you flip G and G inverse, you can switch representatives, right, between these kinds of cosets and the other kinds of cosets. So these are also functions from G mod KZ to FP bar, right? By just changing the coset representative by inverse, you can think of them as functions from G mod KZ to FP bar. And if you look at this function G1, then it corresponds. So these are just functions on the vertices of the tree, right? We go back to the beginning, these are the vertices of the tree. These are not quite vertices of the tree, right? They're actually on the wrong side of it. In the beginning, when you do this, you're a bit vague and you get very confused because you put your cosets on the wrong side. It leads to a lot of chaos. But with a bit of experience, you have to be a bit more careful. Functions on vertices of the tree like this. And what function does this correspond to? It corresponds to the following function. It takes G ZP squared to 1 and all other lattices to 0. For example, the function 1, 1 would take the standard lattice to 1 and it would take all other lattices to 0. So I'm claiming this, that in the bijection between this kind of square bracket notation and functions on the vertices of the tree, this particular function corresponds to this particular function on the tree, on the vertices of the tree. And here's a small check to check that. If you evaluate G1 and G inverse, right, G inverse is coming from the coset representatives, then this is exactly G inverse dot G of 1 by the definition, which is 1 dot 1, which is 1, and all others will be going to 0. Okay, so this little remark here is supposed to help understand why G1 corresponds to this particular function. All right, and over here too we have some natural bijection between an induced space and functions on the oriented edges. So I'm taking again R to be 0. Let's take D0. So again you get functions from G mod IZ, because IZ action was on the left, if you remember, to FP bar. Right? But by this G inverse thing, changing coset representatives, there's also functions like this. And again, what does this particular function correspond to? G1. I'm claiming it corresponds to the following function. It's the function which takes G of the standard lattice, ZP squared, alpha ZP squared, to 1 and all other lattices to 0. All other edges, oriented edges. Okay, so this is the function G square bracket 1. In this notation, it corresponds to functions on the oriented edges in this particular way. And there's a similar check like this with a double square bracket still replaced. This you can. Yes. This is compactly supported because it's taking one particular axis 1, that to 0, and these also everything is compactly supported here. Yeah, functions. Yeah, oh, you mean up here? Yes. Everywhere it's compactly supported. Okay, so good. Now here comes let's try and do this computation. How much time do I have? Hour is finished. Okay, maybe I'll skip this step because I think it'll just take another 15 minutes of computation. I was going to motivate those definitions, the heck operator, using this dictionary. So here, we have defined the heck operator using square bracket functions, right? But because of this dictionary here, you also have heck operators on this side, which are functions of the lattices and functions on oriented edges. So maybe let me just write the definitions down. Yeah, so here on this side you have the sum of neighbor operators. T is sum of neighbor operators. Sum of neighbors operator. So as I said, if you have a vertex, the value of a vertex is all the other vertices formal linear combination of them. That induces an action on the function of the vertices, right? Just add up the values of the function of the neighboring vertices. So on this side, you have an action of the heck operator, T, right? But we also defined an action of the heck operator here by that formal nonsense. And under this dictionary, you have to check that that definition I gave over here is exactly that definition. It's a 15-minute computation, which is done in my notes, and I will maybe skip that. Maybe save a little bit of time.
This bracket here, G, 1, 1.
This is G comma 1 square bracket, double square bracket. There's no, yeah, sorry, there's double square brackets in my diagram. T is sum of neighbors operator on the Bruin tree on the graph. Given a vertex, formally you look at all the neighboring vertices, and given a function, you add up the values of the new function you get is by adding up the values of the function in all the neighboring vertices. So that's a new function, and that's the operator T. So it's a graph theory operator, which is very famous. If you translate it under this dictionary, you will exactly get this formula. So you have to somehow check that these are representatives of the neighboring lattices. Okay, these p lambda 01s and this alpha are the representatives of the neighboring lattices of the standard lattice. Okay, so it's a little bit of check which is done in my notes, but I think I'll skip that. And over here, you also have some natural operators on the graph, and then those natural operators on the graph, if you shift them to this direction using this bijection, you'll get exactly these formulas. Okay, so what are these natural operators on the graph? So let's draw the graph up here. Okay. 0, 1, 2, minus 1. So, what are these operators? So, first of all, on a graph, you can do several natural things. One is you can flip an edge. Right? If you have an oriented graph, you can just flip an edge. Right? That's an action on the edges of the graph. Right? These are functions. These are functions on the oriented edges of the graph. Remember, by that lemma, G mod IZ is the oriented edge. The function of the oriented edges of the graph. If you want to induce an action using geometry on this space, well, every time you have an edge, you just flip it, and that induces action on functions on the oriented edges, right? So there's this natural operator, flip an edge. The operator t minus 1, 0 is the source operator. And the operator t1, 2, so this notation took a while for me to understand, but it becomes much more simple if you look at the graph, is the sync operator. What do these mean? I'll put it in a second. So source operator means what? If you have an edge, an oriented edge, right? Pointing, let's say, from 0 to 1, right? What is the value of the source operator on this? We just formally add up all the edges coming into 0, right? That's a formal linear combination of the edges coming into 0. And similarly, I have an edge 0, 1. What is the sync operator? It's formally all the edges coming out of 1. Okay? So given an edge, p edges come into 0 and p edges leave at 1. The source operator just formally adds up all the edges coming into 0, and the sync operator looks at all the edges coming out of the sync, coming out of 1. That are very natural operators, and they turn out to induce operators on functions on the tree.
How do you decide what is going in, what is going out?
Oh, there's oriented edges. So you know what's every edge has two orientations. So this edge, for example, the value of t 1, 2 of 0, 1 edge, t 1, 2 of 0, 1 will be 1, 2 plus 1, 2 prime plus 1, 2 double prime, right? Like that. It's all the edges pointing in that direction, and there are P of them coming out. Sorry? Image? Flip edge. Oh, flip edge just means if you have an edge like this, then you just take the orientation in the other direction. It just acts on an edge by moving it around, and that induces an action on functions on the edge. It acts on oriented edges by flipping the orientation. Flip orientation of an edge. Sorry? Yeah, so this is what she was asking. If you have T12 acting on 0, 1, the edge pointing from 0 to 1, it is 1, 2 because it's coming out of 1. Remember, this is a sink operator, right? So this is the sink because it's flowing into 1. The water is flowing from 0 to 1, right? This is the sink, this is the source. Gangotri, and where did the Ganga come out? Does anyone know? Bangladesh? Yeah. No Bengalis here? Where does the Ganges flow out? Sundarbans. Yeah, Bay of Bengal. Right. So this is Gangotri, and this is the Bay of Bengal, right? Source, sink. Then from here you have some ships sailing away, right? So this operator, the source operator is all the sinks coming out of the Bay of Bengal, and the sink operator is all the Himalayan waters coming into 0, right? Into Gangotri. All streams coming into 0 underground. Okay, so these three operators are very natural operators on the graph, and they induce operators on functions on the graph. And if you translate, fortunately I wrote the translation down at least, now you can do the exercise. Use this translation, you'll get exactly these results.
You are taking those edges and summing, is it?
Yeah, you take a formal sum. So this is what's the correspondence, not really a function of the operator. The value of a particular edge is the sum of edges. Okay, so on one of my pages of my notes, I worked out some of these things. How these three formulas, or at least I think I did all of them, how these formulas can be derived by just graph theory. You have some graph theory operations on this side, and you just use these dictionaries, and you translate to the other side, and you get exactly those formulas. That's the motivation behind those formulas. Okay, great. So let's move on. Yes. Double prime. Oh, I was just being a little loose here. See, there's two. This is the lattice spanned by E1 and alpha squared E2, which is 1, 0 and 0 p squared. Okay? But there's some other lattices here which are not of that shape and have an index p relation. So I'm just calling them 2 prime, 2 double prime, 2, 2. So all the edges coming out of that. Yeah. There are p of them. 2 is just one of the vertices, but there's 2 prime, 2 double prime, up to 2 p primes. Okay. Any other questions while I'm erasing? Okay, so now we come to basic building blocks. Of representations of G. Again, there's a spherical case and in the Bohori case. I'm going to again try and do both of them uniformly. So I think Shalini had some characters which were multi characters of P star. But it was going into E star, going to FP star, FP bar star, same thing. And I'm going to have some constants lambda belonging to FP bar. So we have an R, which is just a number between 0 and p minus 1. P was a prime, by the way. I forgot to say that at the beginning. Lambda was a non-zero constant, and eta is a parameter. Okay, so again we have two kinds of. Where do I draw this line? I need a lot of space here. Here. Okay, spherical side. This was already in Shani's talk, and the Bohori side. So here is the basic building block of some representations of which you see all the time in the literature, pi r lambda eta. So far what do we have? We're trying to construct representations of GL2QP. We constructed some graph, we constructed functions on the graph, and we had some G representations on them. These big spaces unfortunately don't give irreducible representations. You have to cut them down using the Heck operators. So that's what we're going to do now. So you take compact induction kz to G of VR, and you go modulo the Heck operator T minus lambda. I'll explain that in a second. And you tensor with eta. So you see I've used R, lambda, and eta, everything there. So remember we had this space of functions. These are just functions from G to VR, right? And it had a G action on it, so this was a G module. And we also had some Heck operators, Heck algebra, which acts on this. It's the algebra of operators. So T was one of the Heck operators. So this means the image of this is the co-kernel of T minus lambda. Okay? So T, in this case, it turns out that T is injective, so the kernel is not so interesting. But the co-kernel is interesting. And we're going to look at T. You may as well look at T minus lambda times identity. That's another operator. And I think this will come up in your lectures more. Yeah. So maybe you did it already today or no? You didn't define the Heck algebra today. So anyway, I think the numerators were defined, but the denominators were not yet defined. So we're looking at the operator T acting on this space, and we're looking at the image of T minus lambda, and you take the quotient. That's called the co-kernel, right? So this is a space which is often irreducible. Not always, some exceptions, but it's often irreducible. And you can twist this by, Shalini was more precise, I won't write it here. You take determinant, and then you apply keta. The determinant of a matrix in GL2QP, this is basic building blocks of representation G, GL2QP. Take determinant to get an element of QP star, you apply eta, you get a non-zero dot P number. Right? So you can just multiply it by these scalars here. So these are the basic building blocks in the spherical world. And here is now the theorem of ABC. I'll put A hyphen B comma C because this is Gauri Sagar, ex-student of Anand Vardhan, that was 9 years ago, and Chitra, which is more recent. It was on the archive last year maybe. So here, and this is sort of the punchline of this whole thing, induction I Z to G, D to the R. Remember we had these spaces? In the already world we had these compactly induced spaces, functions into FP bar, but the I Z action was by D to the R. But now we have a whole bunch of operators, right? We have 3 operators. So which one do we go modulo, what do we go mod by? But here's the formula that is part of the theorem. So it says that you have to go modulo T minus 1, 0 plus delta R, Kronecker delta function. I won't write it because everyone knows what delta AB means. It's 1 when A is equal to B and 0 otherwise. T1, 0 plus T1, 2 plus delta R0 T1, 0 minus lambda. And then tensor the whole thing with eta. Okay, so this is the theorem that I wanted to explain today, at least the statement, if I don't get to the proof. So instead of going modulo one of the operators, you go modulo a few of them with some various little bit of subtleties. So the basic thing is that you go modulo T minus 1, 0 always, and you always go modulo T1, 2 minus lambda. Okay, so when you go modulo T minus 1, 0, you get very much the numerators of these spaces. And when you go modulo, and the operator T here is supposed to correspond to T1, 2, so T minus lambda corresponds to T1, 2 minus lambda. So all of this was done in AB. Okay? But the thing that was not done in AB is how to correct this when R is 0 or P minus 1. So here, you have to add on a correction term to T minus 1, 0 and a correction term to T1, 2. The correction term is a T1, 0 term, and that only happens if R is P minus 1. And similarly, you add on T1, 0 to T1, 2 only if R is equal to 0. Okay, so that's the content of the C part of the ABC theorem. And you can rewrite the basic building blocks that occur in Broy's work in terms of Eva-Horry induction. So on this side, you see there's a IZ to G induction, and here there's a KZ to G. Any questions, because it's becoming a bit technical. This is supposed to be one of the highlights of the lecture. Any questions on this?
What is this sum? So you're summing over all the
With sum?
sum of all these things, or
Where
why
is this?
there is a bracket in the first?
This bracket?
Uh,
Oh, this just means the image of this operator.
just separated separately and that
Yes,
part
yes,
is-
yes. So it's bad notation, but it's Roy's notation. He never writes the word image. So when you write it like this, it looks like you can just move things around, right? You can't do that. This is the image of this operator, and this is the image of this operator. Right. So you can't commute things, otherwise it gets a bit confusing. This is also image of T minus lambda. It always looks a bit weird when you first see it, but the co-kernel of T minus lambda. Any other questions? Okay, so that's theorem ABC. Okay, maybe I'll now state we have already mod PLLC. Minutes, I can do it. So all of this is so-called the analysis side of the Langlands correspondence. Everything is discrete, it's like computer science work. It doesn't look so much like analysis, but this is sort of the analytic side of the Langlands correspondence. These representations. The representations of G, which occur on the analysis, or what is maybe more precisely the automorphic side, local stuff, automorphic side of the Langlands correspondence. Now we're going to talk about the Galois side of the Langlands correspondence very briefly, and then I'm going to tell you the Monpi local language correspondence in the Iwahori language, and that will be the end. Okay, so a very brief note on Galois representations. I understand that some of you may not even have done Galois theory ever in your life, so it's a bit weird to start talking about Galois representations if you haven't done Galois theory. So maybe it's a motivation to learn Galois theory very well. It's a very basic and important thing in number theory. And then once you know Galois theory, you have Galois groups, and you have to understand their representation. Okay, so Galois representations. Just basically to introduce some of the notation. So GQP is going to be the Galois group of QP. It's all automorphisms of QP bar, fixing QP. And there are two kinds of representations here. There's omega, well, two kinds of characters that I want to look at. These are fundamental characters of level 1 and level 2. Sometimes called omega 1. There's omega 2, which is a character of a quadratic extension of QP. So here you have QP, and there's something called the unramified quadratic extension of QP, which I'm calling QP squared. If you haven't seen these things, you can ask in the tutorials. Its real integers is something called ZP squared, and its residue field, ZP squared mod P, is a finite field with P squared elements. So it's like FP, but everything with P squared in it. Finite field with P squared elements. There's a row. So these are the fundamental characters. I won't have time to define them. Of levels 1 and 2. And once you have a fundamental character of level 2, yeah, so here I'm being a little bit imprecise. These are actually a character of the inertia groups extended to GQP squared in some way, some property, but I may not get into that. So another kind of these representations will be. So you're looking, so I should back up a little bit. What we want to do on the Galois side is, here we have these infinite dimensional Monpi representations of G, L to QP. Okay, but on the Galois side, we will have finite dimensional representations of the Galois group of QP, which are actually two-dimensional. So on the Galois side, you'll see the number 2 all the time, but it will come in the size of the representations, two-dimensional representations. On the automorphic side, you will also see the number 2 all the time, but it will come in the size of the matrix groups, GL to QP. The dimensions of the representations are infinite dimensional. I want to say this clearly so that at least at the first approximation, you get that much out of it. Okay, the two-dimensional representation on the Galois side, but on the automorphic side, it is infinite dimensional representations, but of GL. There's also infinite. Okay, and there's one representation we can construct out of this, which which is the Galois version of induction. So this is Galois induction from QP squared to GQP of some power of omega 2c. This is the induced representation. And I'm going to assume p plus 1 does not divide c. What is QP star? QP squared. Ah, yeah, okay. Yeah, I was just telling you that. So, Q7 has 3 quadratic extensions. You know, Q has many quadratic extensions. Q root 2, Q root 5, Q root 7, right? Q root 14. But if you localize Q at a prime, QP is odd, then it only has 3 quadratic extensions. 2 of those extensions are a bit more complicated than one of them. That one of them is called the unramified extension of QP. It is not very different from QP. I mean, even the unramified extensions are not very different from QP in some sense, but whatever. Okay, so it's unramified. Let me not try and define what unramified is. But it means that the prime P, if you look at the prime factorization of P upstairs, there's no, if you break it into primes, there's only one prime. Then there's no power that occurs on that prime. Okay, so it's unramified prime. So this is the unique unramified extension of QP, which is of order 2. The reason it's called QP squared, that's kind of a little bit of GT mutation, is that the number p squared is associated with this field because if you look at the ring of integers and you go mod p, then it has p squared elements in its residue field. Finite field with p squared elements occurs there. So we call this field QP squared to recall that residue field as p squared. Okay, so Galois representations, there are also some induced representations in the Galois world, and you can spend your whole life working only on the Galois side. People do. Fact, every 2-dimensional representation, copy representation, I'm not writing that, GQP is of the form mu lambda omega to the A direct sum reducible, I mean semi-simple, okay, I won't write that also, mu omega to the B, or this thing, induction omega 2 to the C from GQP squared to GQP tensor maybe mu. I have too many mu. So what are these characters mu? So I told you what omega and omega 2 was. Here mu x is the unramified character GQP, which takes Frobenius, more precisely geometric Frobenius, to x, and it takes inertia. So some of these words you're going to have to ask in the tutorial. You haven't done much algebraic number theory, you ask these words in the tutorial. So on the Galois side, there's something called the Galois group, GQP, there's something called the inertia group, IQP, and unramified character means on the inertia group it's trivial, but on the full Galois group it may not be trivial. There's one element called Frobenius, which generates topologically GQP mod IQP. Take the inverse of that here, that's how it's normalized, and we map that to X. Okay, so every semi-simple 2-dimensional mod P representation over FP bar is of this form, and I have a more general lemma in the notes about n-dimensional irreducible representations being of this form. Induced, you might be a little worried where this induced representation is. So you can look at the notes. You have to speak louder. There's a big AC here somewhere. Yeah. Yes. Yeah, just yeah. So there's a Frobenius in the mod P world, and you can lift it to characteristic 0 world. That's the arithmetic Frobenius, and the inverse of that is the geometric Frobenius. It's just a notation. Can I erase this? think I can finally state the Evahori mod PLLC, which is what I need. 2 minutes. Okay, 3 minutes, I started in the day. Can finally state the Evahori mod PLLC. Shalini is going to state the usual mod PLLC. Using term ABC, I'm going to state the Evahori mod PLLC. So, should I state the spherical version first or not? Okay, maybe not. So, I'll go straight to the Evahori version. So, when lambda is 0, so Shalini will state the spherical version. I don't have time to do both the columns. I'm doing the right hand side of the column. So, when your Galois representation, so this is the Galois side. Representation of GQP, these are representations of G, which is G of QP. Everything is mod P. So if you have something irreducible, induction from GQP squared to GQP, omega 2 to the C, tensor eta. Although I didn't explain this notation, but I think I did. Did I explain anything? I think I did. U lambda is the unramified character, yeah. So eta now is mu. So the mod P character, and eta is an arbitrary character, maybe even more general than mu. Lambda, mu, and nu were mod P constants. If they get twisted by an arbitrary character, then this corresponds to this particular building block, and if lambda is equal to 0, lambda is not equal to 0, then this representation, every representation is of this form, direct sum of these two characters, but let me take a slightly special case which is equally general. Actually, so u lambda omega to the r plus 1, I should have said here that usual notations, r is between 0 and p minus 1, lambda is an at p bar star, and eta is a character from qp star to the at p bar star. And that's why I was getting confused. I was writing new notation, and this is the notation for this page. Yeah, so this kind of direct sum, reducible representation, mu lambda inverse, tensor eta, this corresponds to where pi r lambda eta is isomorphic to, this is the ABC theorem. Compact induction, I'm repeating this part. I z to g e to the r over that huge thing. Divided by that huge thing, g minus 1, 0, plus delta term. What I wrote just a few seconds ago, G12 plus delta R0. T10 minus lambda, tensor eta. Tensor eta is the right of the fraction on the numerator of the fraction. Lambda was non-zero, so lambda inverse makes sense. Yeah, first case is lambda is 0, it's kind of, so there should be a 0 here. Thank you. And here lambda is non-zero. Lambda inverse makes sense. And you can ask, what are these representations? So these representations also occur in Broy's work. They have some other meaning. I think I wrote them down. I did, right? The building blocks. Yeah, I wrote these representations down in the spherical model. And then I said that they have an Evahori model. And this is the formula for these representations in the Evahori model in all cases. Okay, so this is the we've already modeled local language correspondence. And just to see where these lectures are going, okay, I was going to spend another 45 minutes trying to prove this, but this theorem may be seen, but I think I've run out of time. I definitely have run out of time, so I won't do that, but you can look at the notes. One thing I should say, to see where these lectures are going, because it looks a little technical, you basically, this is a talk about reductions of Galois representations. So just one square I'm going to make. There are these Galois representations called VKL. They're representations of GQP in characteristic 0. They correspond to certain Banach spaces, VKL, under the p-adic local language correspondence, which is on that board. Right? Title of this program, which we haven't talked about at all. Right? We're doing everything downstairs in some sense, but there's stuff happening upstairs also, right? We're on Earth, but there's stuff happening in heaven. So this is heaven, right? But sometimes you want to go from heaven down to Earth, so you want to reduce these representations mod P. These are characteristic as 0 representations. You want to study the reductions of these semi-stable representations, VKL bar. Okay, these are mod P representations of the Galois group of Q. It's a very hard problem. One doesn't know how to do it. So what one does is one goes 3 ways around the square. One first takes the p-adic local language correspondent VKL of this representation VKL, takes the lattice in here and reduces that mod P, so I'll call that VKL bar, or right? And then it turns out that here this is a mod P representation, Galois representation, GQP representation mod P, and this is a GL2QP mod P representation. Okay? And these are related by the Ivahori mod P local language correspondence. Ivahori mod P LLC. Okay? So what I've been describing this whole time is this part of the work. Okay? In this fundamental square, which you should keep in mind throughout these 4 lectures, there's this stuff which will come in lecture 3. And to prepare for that, I'll have to do lecture 2. But I decided to do the bottom of this square, which is lecture 1. Okay, lecture 1 is the mod P local language correspondence. Defined by Breuil, but also you can do it in the overhead setting. So you want to go around this square, you want to look at the Banach space, which will require some definitions in lecture 2, and then more precisely define compute its reduction. You'll wind up getting answers that look like this. Lots of T12s, T-1 zeros in your formulas when you compute the reduction of the Banach space. And then you try and go backwards, or you can go backwards. It turns out this is in the image, the reduction, this is in the image of the mod P. The square commutes. So this is in the image of the mod P, we've already mod P LLC. And this map is injective. It's not subjective, unfortunately. You can see that the break subjective, but so you can go around this way and you can then recover the mod P representation. So this is the goal of the lectures. The title was this part. This left-hand vertical arrow can be explained by working in lecture 4 on this side, lecture 2 and 3 on this side. Yeah, so it's not very. The order is a bit strange, but 1, 2, 3, and 4. Okay, those are the parts of the lectures that I'm trying to explain.